Hi, everyone. This is part 3 of lecture 5 on interpreting differential privacy. So this part of the lecture is about the interface between math and the mathematical definitions we write down and the real world concepts we're trying to capture. Okay, so mathematical formulations of real world social concepts, like privacy, are tricky. And there's never going to be a single correct definition. And that's because a concept like privacy means different things to different people and it really captures a whole host of context dependent ideas, which may vary from, which really mean lots of different things and have many facets to them. Okay. So at best, a mathematical definition can capture and help us understand one aspect. Sorry, there's a typo on the slide. One aspect of a real world concept. Okay, and what I'd like to explain is why I think differential privacy does this uh, and why. So if we wanted to interpret like what guarantee differential privacy gives us, a natural approach is to say that differential privacy is about stopping someone on the outside who sees the outputs of an algorithm from learning too much about individuals in a data set. So if you wanted to like formulate that, maybe that intuition a little more crisply, we might try something like this. Like suppose you are an attacker and I am a person in the data set. We might hope something like the following, that your beliefs about me should be the same after you see the output of the algorithm as they were before you saw the output of the algorithm. Okay, so this is a natural type of thing to want to say. I mean, basically, it's trying to kind of put its fingers on the concept that you learn nothing about me from seeing the output of the algorithm. And it is indeed the kind of thing that we can achieve, say, in cryptography with like encryption. But in the context of publishing statistics about a bit, or running machine learning algorithms or whatever it is on a data set, it turns out this notion is impossible to achieve. Okay, and it's impossible in basically in any context where you're releasing useful information, even very aggregate information about the data set. So let me explain why this is via a story. All right, so imagine it's like, the 1960s, first episode of Mad Men. Smoking is cool. And suppose you know that I smoke. Okay. Now, a priori, just knowing that doesn't necessarily make you think it's more or less likely that I have or will develop lung disease. But suppose you now see some clinical study. You see the outcome of the output of some clinical study that shows that smoking and certain forms of lung disease are strongly correlated. Suddenly, you learn something about me, right? In particular, you learn that I'm a bad health insurance risk and maybe that you should charge me a lot more for health insurance than you were before. But this thing you've learned about me, it's definitely changed your view of my data, but it hasn't changed. It hasn't changed because my data were there in the study. It's changed because you learned this fact about human biology. Right. So we can't hope to say you learn nothing about me, because anything that teaches you something about the world is going to, along the way, very possibly teach you something about me. So differential privacy can't hope for that strong guarantee at the top of the slide, but it can hope for something weaker but still meaningful, which is the following: that no matter what you know ahead of time, you learn almost the same things about me, whether or not my data are used in the study. So this is a much more subtle type of assurance that I'm getting about what you learn, right? So it's not that you learn nothing, but it's that you learn whatever you learn is not specific to my data record being in the data set. Okay, so it's instructive to try to pin this, the text in the green box to pin this thing down mathematically. And it'll help us, for example, think about variations on the definition of differential privacy. In order to pin it down mathematically, though, we're going to need to nail down what we mean by sort of, some of these words here. We're going to need to nail down what we mean by what you know ahead of time, by what you learn, and what you learn, like when my data are used and when my data are not used. Okay, so this is sometimes called the Bayesian interpretation of differential privacy. If you're not familiar with the word, it doesn't matter. It just has to do with, basically the mathematical framework. All right, so suppose you're an attacker, and we want to model your background knowledge. So we're going to do this by writing down or imagining we can write down a probability distribution on X that captures everything you know. So this probability distribution reflects how likely you think the different data sets are. Okay. So this should fold in like whatever other data sets you have access to, or other knowledge about the world or biology or whatever it is. We also need to nail down what it means to say like what you learn about me, or what you learn about the world, like what conclusions you draw based on the output of the algorithm. Okay, so we can model this simply via the posterior distribution, namely, on input, given the output A, we can now, and a probability distribution on the input, we can now compute, the conditional probability of X being equal to any particular data set, given this output A. And we can do that because we have a complete description of the algorithm, right? With a differentially private algorithm, that the algorithm itself is clearly described, and it's basically gives you the randomization of the algorithm, randomness in the algorithm gives you for each data set, for any given data set X, the probability distribution on outputs. So that's exactly what you need to compute this conditional distribution. All right, so what we're going to do is think about how does this conditional distribution evolve in like a few different worlds. So the first world, first experiment we'll consider is where we just run the algorithm on the basic data set, on the real data set. So this is like just the plain vanilla world. But then we'll also consider n other experiments, and specifically for every index I, we'll consider what would happen if we were to run the algorithm on the data set X from which person I's data had been removed. And it doesn't really matter how we do that removal really, but like a simple thing to do is to imagine we'll just, replace person I's data with some default record. Let's say the all zeros string, or maybe the empty string, or whatever it is. Okay. All right, so now we've got experiment 0 and these other experiments, one for each person, where that person's data have been removed. And the theorem that we can prove is that if an algorithm is epsilon differentially private, then for every index I and for every output A, the conditional distribution you get in experiment 0 is going to be essentially the same as the conditional distribution you get in experiment I. So in English, you'll draw essentially the same conclusions when my data are used than when, as you would have drawn had my data not been used and you'd been even told that my data were not used. So what is it, just to sort of finish stating this theorem carefully. So this notation, this like two distributions are similar up to epsilon, that is actually, that's not a notation we've used so far in the class, but it's a reasonably standard one in this literature. And it's a notion you've seen already in the context of differential privacy. So we'll say P and Q are epsilon multiplicatively close. It's often the way it's pronounced. Okay, so they satisfy this relationship on the slide. If and only if for every event in the output space, so if these are two distributions on the same output space, the probability of E under P is less than E to the epsilon times the probability under Q, and vice versa, the probability under Q is less than E to the S, or no more than E to the epsilon times the probability under P. Okay, so this is exactly the like notion of closeness we use to define differential privacy. And now it's what comes up in this theorem. So what the theorem says is no matter what the prior distribution is, then we get this guarantee that the conditional distributions an adversary would form in the real world and in a world where personalized data were not used, those two conditional distributions are about the same. So I'm not going to prove this. We're actually going to prove it as a part of an in-class exercise. But it's a, it follows more or less directly from the definitions. One way to think about it is that I'm in both cases, I'm using Bayes' rule to compute some conditional distribution. In the first case, I'm using this prior distribution that captures the adversary's initial knowledge and the output A, and I'm using these the thing I'm using for the probability of A given X is the probability that the algorithm on input X would produce A. And then in the other case, the thing I'm using is the probability that the algorithm A on input X minus I, so there should be an I there at the bottom of the slide, is equal to A. Okay. All right. So so this is one like mathematical way to kind of nail down that text in green that I had. And it helps us understand, for one thing it helps us do is to think about variations on the definition of differential privacy. So as an example, suppose we were to consider an additive variant of differential privacy. So differential privacy requires that probabilities change by small multiplicative amounts. But what if I wanted to just allow an additive deviation in the probabilities? So that would look something like this. For all neighboring data sets X and X prime, for all events E, the probability that A of X lies in E is at most the probability that A of X prime lies in E plus delta instead of times E to the epsilon. Okay, so I've changed the symbol from epsilon to delta because it's a different, this number means a different thing. So we could like write down this definition. In fact, I just did. And this definition actually satisfies lots of nice properties. So it turns out, you can argue it satisfies composition. It satisfies, just like we had in part 1 of the lecture, post-processing, group privacy, or like, this parameter delta increases not too quickly as you consider larger and larger changes between X and X prime. But it turns out this definition is like a terrible definition as written here. And I'm going to try and explain why that is. But like in particular, it will not satisfy anything like this Bayesian interpretation. Okay, like you won't be able to prove a version of the theorem we had on the previous slide, theorem 3 in the notes. At least not when delta is a lot bigger than 1 over n. Okay, when delta is much smaller than 1 over n, then you might actually be able to say something meaningful, and we'll talk about that later in the class. But when delta is big, you're not bigger than 1 over n, then you're not going to get anything meaningful out of this. And indeed, useful outputs for this type of algorithm are possible only if delta is bigger than 1 over n, just like with differential privacy. And that's because, like, if you change n records, the distribution changes by an additive delta times n at most. So if delta is much smaller than 1 over n, then you're hosed. You're not releasing any, your algorithm has to behave essentially the same on all possible data sets. Okay, so let me try to convince you that this definition as it is when delta is big is like a bad definition. And I'm going to do it just by giving you an example of something that satisfies the definition that you would never want to use. Okay, and I'll call this the name and shame algorithm. All right. So this name and shame algorithm, what it does is it just passes through the data set and decides independently for each record to either publish the record in the clear or not publish it. And it publishes each record in the clear with probability delta, and it fails to publish it with probability. It decides not to publish it with probability 1 minus delta. Okay, so for each record, it either publishes like, hey, you know, something that basically is saying person I's data is blah, xi, or like this special symbol that just means I'm not telling you anything about person I. Okay, so like basically, you know, if this is my data set, I'm going to end up selecting some subset of the records, each one independently with probability delta, and just publishing them in the clear. Okay. So notice, of course, that this is like a terrible thing to, you know, terrible way to protect privacy, right? This mechanism outputs, you know, some person's data in the clear with high probability. In fact, like a bunch of people. Okay, if delta is a lot bigger than 1/n, then, you know, I'm going to essentially publish about the records of about a delta times n people from the data set. So those people are getting, you know, completely badly treated. They have no kind of privacy at all. And so that's why this is like not a good mechanism. I wouldn't, you know, recommend this as a good way to like protect sensitive data at all. And notice that this type of mechanism like shows why it would be impossible to prove that a theorem like that Bayesian interpretation we had two slides back. And that's because for the records that get published, the attacker learns way more than they would have had person I's data been removed from the data set, right? For the you know, if Alice is one of the people whose record gets published, then the adversary's beliefs about Alice change in this like very precise, you know, clear way, that they, you know, which they would not have if Alice's record had been redacted before running the mechanism. Okay, so what have we got? We've got that, in particular, like it's not a good idea to you know, differential privacy if you want an additive change to the probabilities instead of a multiplicative change on its own. It's not a very good approach, and that's because if you want this mechanism to be useful, this delta parameter has to be big, at least, you know, at least 1/n, a lot bigger than that, really. And then you're in this regime where there are like terrible mechanisms that satisfy the definition. And you know, one way, and so this theorem that we have on this slide here, it is one way to distinguish among these different variations on differential privacy. If you can prove a theorem sort of like this one, then you know you've got your hands on something more meaningful. Okay, and we may revisit this topic later in the class, but that's all for now.